In this video, we're going to go over some practice problems relating to nuclear chemistry. So let's start with this one. How many protons, neutrons, and electrons are present in mercury 201? So for each of these problems, feel free to pause the video and try it out yourself. So the symbol for mercury is Hg, and the mass number is 201. Now we need to find the atomic number, and we could do so using the periodic table. The atomic number of mercury, if you look it up, it's 80. Now, the atomic number tells you the number of protons. The mass number is the sum of the neutrons and the protons. So to calculate the number of protons, it's always going to be the atomic number, which is 80. And so that's the first answer. Now to calculate the number of neutrons, it's the difference between the mass number and the atomic number. So the mass number is 201. The atomic number is 80. So 201 minus 80, that's 121. And so that's how many neutrons are present in mercury. That is, of course, this particular isotope of mercury. Now, what about the number of electrons in mercury 201? For an atom, the number of protons and electrons is the same. Now, we weren't given an ion, so we're assuming this is an atom. So we're going to say it has 80 electrons. Now, let's say if we had the mercury 2+ ion, then the number of electrons would be 78. The +2 charge tells us that there's 2 more protons than electrons. But for atoms, the protons and electrons are the same because atoms are electrically neutral. Now, how many nucleons is present in mercury 201? Nucleons are the subatomic particles in the nucleus, such as protons and neutrons. So the mass number tells us how many nucleons are present, so it's 201. We have 80 protons and 121 neutrons. If you add that up, that gives you 201 nucleons. Number 2, which of the following is an alpha particle? So let's go through each one. Answer choice A represents a gamma particle. This is a high energy photon, and it has virtually no mass and no charge. So it's not A. Now B represents an electron, also known as a beta particle. It has a mass of virtually 0 relative to protons and neutrons. It's very light, and the charge is -1. Next, we have the antiparticle of an electron, known as the positron. So the positron has the same mass of an electron, but with an opposite charge. The charge is +1 as opposed to -1. Next, we have the alpha particle, which is the nucleus of a helium atom. It has 2 protons, 2 neutrons. So as you can see, it has a mass of 4 and a charge of 2, which is also the atomic number for elements as well. So D is the answer. And then E represents a neutron. A neutron has a mass of 1 and a charge of 0 because it's neutral. And the alpha particle, you can also write it this way, with an alpha symbol instead of the helium symbol. Now there's one other particle that you need to be familiar with, and that is the proton. The proton has a mass of 1 and a charge of 1. So just make sure you know these particles because you'll need them for other problems coming up soon. Number 3, what element will be formed if thorium-230 undergoes alpha decay? So this particular isotope has a mass of 230, and thorium has an atomic number of, it's right next to uranium. The atomic number of thorium is 90. So it undergoes alpha decay. What's going to be the missing element? Now, when balancing a nuclear equation, you need to make sure that the mass is the same and the charge remains the same. So 4 plus what number is 230? 230 minus 4 is 226, and 90 minus 2 is 88. So therefore, if thorium-230 undergoes alpha decay, it's going to produce what element? The atomic number always identifies the element. So if you go to the periodic table and look for an element with an atomic number of 88, you'll see that it's radium, Ra. So that is the element that will be formed if thorium undergoes a single alpha decay event. Number 4. What element will be produced if iodine-131 undergoes beta decay? So let's write a reaction. So we have a mass of 131, and based on the periodic table, iodine has an atomic number of 53. So it undergoes beta decay. That means it produces a beta particle or an electron. So we have to put that on the right side. So what is the missing element? 131 minus 0 is 131. And then negative 1 plus what number adds up to 53? Negative 1 plus 54 adds up to 53. And element 54 is xenon. Xenon has an atomic number of 54. So that's the element that will be produced. Number 5. Which of the following processes converts a neutron into a proton? Let's go through each one. Let's start with alpha decay. Uranium-238 undergoes alpha decay to increase its stability. Now, if it undergoes alpha decay, what is the missing particle, or what is the element that's produced? 238 minus 4 is 234, and 92 minus 2 is 90. Now let's analyze the number of protons and neutrons. This is, by the way, thorium-234. Thorium always has an atomic number of 90. Thorium-234 and thorium-230, they're isotopes of each other. They have the same number of protons but different number of neutrons. Now uranium-238 has 92 protons. Thorium-234 has 90 protons. The atomic number gives us the number of protons. Now the number of neutrons is the difference between a mass number and the atomic number. So 238 minus 92 is 146, and 234 minus 90 is 144. So notice that the number of neutrons decreased by 2, and the number of protons decreased by 2. So alpha decay will always decrease the number of neutrons and protons by 2, so it decreases the mass by 4. It doesn't convert a neutron into a proton. It simply reduces the number of neutrons and protons in an element. So it's not going to be alpha decay. Now let's take a look at positron decay. Let's start with sodium-22. It undergoes positron decay and it produces neon-22. So we can see the mass and the charges are balanced. Now, sodium has 11 protons and 11 neutrons. Neon has 10 protons, 12 neutrons. So notice that the number of neutrons increased by 1, and the number of protons decreased by 1. So that means that a proton was converted into a neutron because the number of protons went down by 1 and the number of neutrons went up by 1. And so positron production, it decreases the number of protons but increases the number of neutrons. But we're looking for something that converts a neutron into a proton and not a proton into a neutron. So B is eliminated. Now what about gamma decay? So let's say if we have an energetic element, let me use an example. Let's use sodium 22. But let's say it has a lot of energy and it emits some of that energy in the form of gamma radiation. Notice that gamma decay does not change the mass or the atomic number. So therefore, it's not going to convert a neutron into a proton. Gamma decay simply reduces the energy of the nucleus. Now let's talk about beta decay. And I'm going to use iodine 131. When it undergoes beta decay, as mentioned before, it's going to give us xenon. So iodine has 53 protons, xenon has 54 protons. And then 131 minus 53, that's 78 neutrons. And 131 minus 54 is 77 neutrons. So the number of protons increased by 1, and the number of neutrons decreased by 1. So we could say that a neutron was converted to a proton since the number of neutrons decreased by 1 and the protons increased by 1. So D is the answer we're looking for. So beta decay will convert a neutron into a proton. Now let's take a look at electron capture. And so I'm going to use mercury 201 for this example. Now for electron capture, the electron has to be on the left side as opposed to the right side. And so what happens is the nucleus captures one of the inner core electrons and a nuclear reaction occurs. 80 plus -1 is 79. And so gold has an atomic number of 79. Mercury has 80 protons, gold has 79 protons. And mercury has 121 neutrons, and gold has 122 neutrons. And so we can see that the number of protons decreased by 1, the number of neutrons increased by 1. So in this example, a proton was converted into a neutron. And so we can eliminate electron capture. So D is the answer. Beta decay converts a neutron into a proton. In this example, uranium-238 is struck by a neutron, and as a result it produces 3 alpha particles, 2 beta particles, and some missing element. What is the unknown element? Well, we need to balance the equation. So let's balance the mass numbers first, and then we can balance the atomic numbers and the charges. So on the left side, focusing on the numbers on top, the mass numbers, it's 238 plus 1 on the left side, and that has to equal to the mass on the right side. So we have 3 alpha particles, each with a mass of 4, so that's going to be 3 times 4, and the mass of the beta particle is 0, and let's say x is the mass of the unknown element. So 238 plus 1 is 239, and 3 times 4 is 12. So x has to be 239 minus 12, which is 227. So that's going to be the mass of the unknown element. Now let's calculate the atomic number of the unknown element. So focusing on the bottom numbers, on the left it's 92 plus 0, and then that's equal to 3 times 2 plus 2 times -1 plus some unknown letter or unknown value y. 3 times 2 is 6. 2 times -1 is -2. And 6 minus 2 is 4. 92 minus 4 is 88. So that's going to be the atomic number of the element. And that corresponds to Ra, radium. So that is the unknown element in this example. Radium-227. Number 7. Which of the following elements will most likely undergo radioactive decay? So how can we tell? Is it going to be carbon-12, nitrogen-14, carbon-14, oxygen-16, or neon-20? Well, you need to know that the element that will undergo radioactive decay, or we could say the isotope. These two are isotopes. They are made up of the same element, but they have different mass numbers. So the isotope that will undergo radioactive decay is the one that is the least stable. So we need to look at the stability of the nucleus. And for light elements, if the neutron to proton ratio is approximately 1, the nucleus will be stable. So all of these are light elements. We're not talking about heavy elements. For heavy elements, the neutron proton ratio is above 1 when it comes to stability. It's slightly above 1. But for light elements, it's approximately 1. So let's analyze carbon-12. Carbon has an atomic number of 6. And so in this example, carbon has 6 protons and 6 neutrons. So 6 divided by 6 is 1. So the neutron-proton ratio is 1 for carbon-12. So we could say that carbon-12 is stable. It's not going to undergo radioactive decay. Nitrogen-14. Nitrogen has an atomic number of 7 if you look at the periodic table. And so it has 7 protons and 7 neutrons. 7 over 7 is 1. So it too has a neutron-proton ratio of 1. Now let's look at carbon-14. It has 6 protons, and 14 minus 6 is 8 neutrons. 8 divided by 6, that's 1.33. So therefore, carbon-14 will likely undergo radioactive decay, and it does. Now what about oxygen-16? Oxygen has an atomic number of 8. It has 8 protons, 8 neutrons, and so it has a neutron-proton ratio of 1. And neon-20, neon has an atomic number of 10, and so it has 10 protons, 10 neutrons, and so the NP ratio is the same. So because carbon-14 has the highest neutron to proton ratio, it will most likely undergo radioactive decay. Number 8. Which form of radioactive decay will carbon-14 use to increase its nuclear stability? Is it going to be alpha decay, positron decay, gamma decay, or beta decay, or even electron capture? So we said that carbon-14 has a neutron-proton ratio of 1.33. And we need to pick the form of decay that's going to decrease the neutron-proton ratio from 1.33 to 1. Because light nuclides, they prefer to have a neutron-proton ratio of approximately 1. So we need some form of decay that's going to decrease the neutron number and increase the proton number. So let's go through alpha decay. So let's assume carbon-14 goes through alpha decay. And so the mass number will be 10, the atomic number will be 4. And beryllium has an atomic number of 4. So beryllium has 4 protons, 6 neutrons. So 6 divided by 4, that's 1.5. So that's not good. The neutron-proton ratio went up, which we don't want. So it's not going to be alpha decay. It's not going to decrease the neutron-proton ratio for this light nuclide. So what about positron production? Let's try that. So a positron is basically the antiparticle of an electron, just with a positive charge. And so the mass is going to be the same, but the atomic number is going to be 5 now instead of 6. And 5 is for boron. So we have 5 protons, 9 neutrons, and 9 divided by 5, it's a big number, it's 1.8. So that's not going to happen. Positron production will make the nucleus less stable. So we can't use that. Now let's jump to E, electron capture. If we try electron capture, it's going to have the same effect as positron production. We're going to get the same particle. And just keep in mind, for electron capture, you got to put the electron on the left side. So the neutron-proton ratio will still be 1.8 for this one. so we could eliminate E. Now for gamma decay, nothing's going to change. We're still going to have carbon-14, and so it can't be gamma decay. So by default, it has to be beta decay. So let's see what's going to happen. So we need to put the electron on the right side. The mass number will still be the same. -1 plus 7 is 6. So we have nitrogen 14. So carbon-14 has a neutron-proton ratio of 1.33. Nitrogen has 7 protons, 7 neutrons. So the neutron-proton ratio is 7/7, or 1. And so beta decay is the ideal mode of radioactive decay for carbon-14. It decreases the neutron-proton ratio from 1.33 to 1. So therefore, it increases the stability of the nucleus. Number 9. Which of the following elements will not undergo radioactive decay? Now, what you need to know is that elements with an atomic number of 84 or more are not stable. They will undergo some form of radioactive decay. Radon, which has the symbol Rn, has an atomic number of 86. Uranium has an atomic number of 92, and thorium is 90. Radium has an atomic number of 88, and it has the symbol Ra. Now lead has an atomic number of 82, and it turns out that lead-206 is stable. It does not undergo radioactive decay. But everything else, thorium, uranium, radon, radium, they all undergo radioactive decay at different rates. But this one does not. So A is the answer in this problem. So keep that in mind. Heavy elements with an atomic number of 84 or more are not stable. They will undergo some form of radioactive decay. Number 10. What is the difference between nuclear fission and nuclear fusion? And feel free to give some examples. So let's start with fission. Fission is the process where we take a heavy element and break it up into 2 lighter elements. So a good example is uranium-235, which is bombarded with a nitrogen. I mean, not a nitrogen atom, but a neutron. So if we shoot a neutron at uranium, it's going to break up into smaller elements. So we have a large element fragmented into smaller pieces. And it creates 3 other neutrons in the process. So that's fission, taking a large heavy element and breaking it up into 2 smaller elements, also known as daughter nuclides. Now, is this process or this chain reaction, would you say it's subcritical, critical, or supercritical? So which of these 3 words would you describe this particular chain reaction, and why? Now, a subcritical reaction will produce less than 1 neutron on average. A critical reaction, which is self-sustaining, will produce 1 neutron for every neutron consumed. And a supercritical reaction will produce more than 1 neutron, and so it's going to expand and accelerate. In this case, this is a supercritical reaction because it uses up 1 neutron, but it produces 3 neutrons, and so the reaction will accelerate at a greater rate. So it's a supercritical chain reaction. Now let's move on and talk about fusion. So what is the difference between fission and fusion? In nuclear fusion, it's basically the reverse of fission. So lighter elements are combined to form heavy elements. And here's a simple example. 2 hydrogen atoms can combine to form an isotope of hydrogen known as deuterium. And a good example of where to find a nuclear fusion reaction is to look up in the sky. You see it every day, and it's the sun. The sun is powered by nuclear fusion. It generates a lot of energy. The sun takes lighter elements like hydrogen and combine them into heavier elements like helium. So hydrogen is the fuel of the sun. And so that's the basic idea behind nuclear fusion, the process of combining lighter elements into heavier elements, generating a lot of energy in the process. 11. The half-life of oxygen-15 is 2 minutes. If there are 320 grams of oxygen-15 in a sample, how many will remain after 10 minutes? So, what do we need to know about the half-life? The half-life is the time it takes for half of the substance to decay, which means half is going to be left over. So we have 320 grams of oxygen-15, and the half-life is 2 minutes, so in 2 minutes, half will remain. So we're going to have 160 grams of oxygen-15. And in another 2 minutes, we're going to have 80 grams of oxygen-15. And then after another 2 minutes, it's going to be 40 grams. And then after another 2 minutes, half will remain. So it's going to be 20. So far, 8 minutes have passed by. So we need another half-life. And then after another 2 minutes, it's going to be 10 grams. So this is the answer. So that's how many grams of oxygen-15 that will remain after 10 minutes.